Okay, in this video we're going to be discussing resonance and why it's important in organic chemistry. You'll see it come up over and over again. It'll help us predict basically what's going to happen in certain situations with mechanisms and basicity, acidity, things like that. So if you remember from general chemistry, we can draw a Lewis structure of any given compound, and we can move electrons around just depending on where the electrons are in the molecule. So for example, with the acetate ion, which is acetic acid, it just has lost a proton, which is indicated by this negative charge here on this oxygen. We can show these electrons come down and these electrons come up. When we do that, we get this second structure here. These both represent the same molecule, just drawn a little bit different way. We can take the combination of these two things and show it look like this. This is more the true, what the true molecule looks like as this resonance structure. And if you notice, we went from a total -1 charge on this oxygen to a total -1 charge on that oxygen. The resonance structure allows us to move that electron between two of the oxygens. So each oxygen carries half of the charge. Compare that to isopropyl alcohol that has lost its proton here. This has no resonance. The reason for that is if we tried to move electrons into this alkyl group, we would break the octet rule for any of these carbons. And so what we say is that these electrons are localized, or they're stuck on this oxygen. And that increases the negative charge concentration in one area, which, comparing that once again to this molecule, that negative charge is distributed across two oxygens. So the electron density became delocalized in this molecule, and it's localized in this molecule. That's important when we consider basicity. So which of these two would be more basic? And why would they be more basic? Well, if we think about it, increasing the amount of electrons in one little spot would mean that they can more readily accept something that is electron poor. The electrons are more willing to make bonds, if you will. Whereas if you have something that's not charged at all, it doesn't have extra electrons to move around, it wouldn't be reactive. So we have a spectrum from a total negative charge to no charge at all. And then we say, well, which one's more basic? Well, the one that's more like something that doesn't have a charge. So this one has far less charge than this one, and so we would predict that this would be less basic than this one. If we look on the pKa table in the book, we will see that as well, that the pKa for carboxylic acids is anywhere from 3 to 5, whereas in the alcohols or water, we see the pKa's ranging in the 15 to 16 area. So the moral is that when we decrease the charge on an atom through resonance, we decrease its basicity. Another way to look at that is if we increase the charge on an atom, like in this case, then the more basic it becomes. And the same thing would hold for a positive charge. If we were to compare water to hydronium, we see that this one has a plus charge, and we often refer to this as a strong acid. And a lot of that is simply just partly due because of the charge on these molecules. Don't forget our lone pairs. And that's more or less resonance. And like I said, in the future you're going to see this applied to certain reactions where you're going to have to know what's more basic or more acidic, and resonance a lot of times can help us make those predictions and understand what's going on.